So in the last class, we established a mapping between the two groups SU2 and SO3. This is the result we obtained in the last class. So corresponding to every element in SU2, we can write down one element in SO3 like in this way. Okay. This we have shown by introducing two spaces. One is R3 and another is TH2 space. So we then connected the objects in these two space, and then using transformations in TH2 space, we find out what is the corresponding transformation in R3. And we established that for this unitary transformation by this unitary matrix in TH2 space, that corresponds to, by our definition of the correspondence between TH2 and R3, this matrix corresponds to this matrix. Now, that means given three numbers alpha, beta, gamma, you can write down a SU2 matrix U. Using the same, for the same values, you can have a SO3 matrix R. Okay. Both of them require three real parameters for specification. So these are the three real parameters. With this, we can either write this or this, and we notice that because of this gamma here, alpha, beta, gamma here, and here they appear in the form of 2 alpha, 2 beta, 2 gamma of trigonometric functions. Therefore, we can write like this: u of alpha plus pi beta gamma, or u of alpha beta plus pi comma gamma, or u of alpha beta gamma plus pi, or in general u of alpha plus pi comma beta plus pi comma gamma plus pi. All these things is equal to minus u of alpha beta gamma. Clear? Because by shifting every parameter by pi, this each matrix gets a -1 sign. Okay. So this whole, so clear? So pi is not the periodicity of this matrix, because if it would have been the periodicity, we would have get same u, not minus u. But for R, we get R, so I am writing one equation, R alpha plus pi, comma, beta plus pi, comma, gamma plus pi, comma, that is equal to R alpha beta gamma, not minus R. Because alpha plus pi will make this 2 alpha plus 2 pi, so that will remain, all this cos sign remains same. So pi is the periodicity of this matrix, but not of this. Rather, we see that two values of alpha, one is alpha, another is alpha plus pi, correspond to two different matrices of SU2. Clear? Two values of alpha, two sets of values of alpha or beta or gamma or both or all the three, separated by pi, would give you two different elements of this set, because this is u, this is minus u. They are different. U and minus u are different. This u plus alpha plus pi, this element is different from u alpha beta gamma, because it's minus of this. But those two values would give you the same R. That means elements of this SU2 matrix, suppose one corresponding to alpha beta gamma and another corresponding to this, which both of them are different matrices, two elements of SU2 matrix correspond to a single element of SO3. Is it clear? Hello?
Yes, sir.
So, one element of SO3, that is R, that two different elements of U whose parameter values are separated by pi are mapped to the same one element of SO3. So the mapping represented by these two sets of equations, this thing is not an isomorphism. It is a homomorphism in general, because it's not one to one. Okay. So it is often said like this. Now, when alpha, beta, gamma, all of them independently start varying from 0 and comes to a value pi, what you get? 0 to pi, it varies. For 0, you have this identity. For alpha, beta, gamma equal to pi, you also have same identity, because 2 gamma, 2 alpha, 2 beta are just 2 pi, which is equal to 0 for trigonometric functions. So when alpha, beta, gamma varies from 0 to pi, by varying alpha, beta, gamma continually independently from 0 to pi, all possible ways, you generate all the elements of SO3. Okay? Because 1 again comes back to 1, and in between alpha, beta varies continually. So therefore, cos 2 alpha, cos 2 beta, cos 2 gamma varies continually from respectively 1 to again 0, again to 1. Okay, because therefore all the elements of SO3 are generated by this variation, but so SO3 is completely generated. All the elements of the group SO3 group is fully generated. But if you come from 0 to pi, SU2 group is not fully generated, because this is not the same as this, and you can easily see one will become identity alpha. For alpha, beta, gamma 0, it is identity. For this pi, this will become alpha, beta, gamma 0, but varying up when it comes to pi, it becomes minus identity. Again, when it varies from pi to 2 pi, then it again goes from minus identity to identity, then fully generating all the elements. Therefore, when it again varies from pi to 2 pi, pi to 2 pi, alpha, beta, gamma, zero to 2 pi, and then pi to 2 pi, SO2 is fully generated. Sorry, SU2 is fully generated. But because of this variation, because of this half variation, SO3 group has been fully generated. Because of this rest up, as it moves from pi to 2 pi, again the SO3 group all the elements will be generated, because for pi it is 2 pi. Again, when it goes to 2 pi, this is 4 pi. So all the elements of the group are twice generated. So when you vary alpha, beta, gamma from 0 to 2 pi, once you vary from 0 to 2 pi, SU2 is fully encompassed. But as you vary from 0 to 2 pi, SO3 group has been generated once, again generated. Is it clear? SO3, because every element correspond to there are two elements corresponding to same SO3. This is another way of seeing like this. So that this is for this reason SO3 is called double cover of SU2, because once you fully generated SU2, the corresponding mapping SO3, corresponding homomorphism SO3, all the elements of this SO3 has been generated twice. Okay, so this is another way of saying this. Okay, so may I proceed?
Yes, sir.
Yes, sir. Yes, sir.
So you can think this half. One half is fully mapped into this, other half is fully mapped into this. This is SU2, this is SO3. Clear? Now you can check that SU2, generators of SU2 satisfy an algebra which is Lie algebra. Now can you tell me what is the generator of SO3? What will be the algebra of the generators? That is also a Lie group, continuous group, SO3, because 3 cross 3 rotation matrices. Now, anyone? Well, what is the generator of, in classical mechanics or in quantum mechanics, what is the generator of rotation?
Angular
momentum. So orbital angular momentum in real space rotation, that is called orbital angular momentum. That also satisfies the same Lie algebra, because Li Lj is I epsilon ijk. So SO3 and SO3 and SU2, though apparently look different, they have a similarity in their structure constant. Their structure constants are same. I am sorry, because in last class I remember in some place I just uttered the word that they have different Lie algebra. That is, I mean, that's slipped off. I mean, that is not correct. They have same Lie algebra. Clear? But this is a group of SO3. This is a group of SU2. And there is a mapping between these two. So everything of content of this group, all the content of this group can be expressed in terms of SO3 and vice versa. Only thing is that there is a degeneracy here. Okay. So let's start today.
Sir, sir, how this doubly connectedness appears in this algebra?
In this
Lie algebra of SO3.
That's a good question. Because this let me think. SU2 has 3 generators. That also has 3 generators. So in terms of the generators, I don't think you can okay, let me think and I will answer later. Okay, I have to think. I have not never thought it because
in case of SU2, the algebra is commutator of sigma I by 2, sigma j by 2 equals to I by 2 epsilon ijk sigma k by 2. But in the case of SO3, is there any half term?
No. That half term is your convention. You could have taken the other way around. I mean, sigma I comma sigma j commutator 2. Then that 2 is include. You can include that 2 factor inside the new structure constant and can define structure constant as 2 epsilon ABC like that.
Oh, okay.
So it is not that doubly connectedness may not be visible in the algebra of the generators, I think, because the algebra of the generator tell about the structure of the groups, and here it is saying that that identical structure of the group is same, but the fact that they are different dimensional matrices, they apply in different spaces. From there you there you find out there you see the doubly connectedness. Whether that doubly connectedness is seen in the algebra of the generators, how it can be seen, I don't see anything, because it is only structure constant and the generators. There is no parameters here. Still, I will think more because, okay, remind me later. Okay.
Okay, sir.
Okay. Now, that means if you do any transformation in just a minute. Hello. Yeah, this class just started. I'll call you after the class. No, sorry. No, what I'm saying that in these okay. So I will come to this later. Let us do this. Let us study this SU2 group. So SU2 group, its element is, each element of SU2 can be written as sum over J, where all the J's are traceless Hermitian matrices of the order of 2 by 2, and JA JB commutator is I epsilon ABC JC. Okay, there are 3 such matrices of the order of 2 cross 2. Now, suppose if it is possible to find an n cross n matrix where n need not be 2, it may be 2, maybe greater than 2. For n cross n, find 3 n cross n matrices J1, J2, J3 such that all are n cross n matrices such that it satisfies these algebras, same Lie algebra, then this matrix which is now an n cross n matrix, this matrix, all possible such matrices, set of all such matrices corresponding to all possible values of alphas, they form a matrix of 3 cross 3, but that group, its order is 3 by 3, but it satisfies the algebra of Lie algebra same as SU2. Then in that case, this object, which is an n cross n matrix, we call an n-dimensional representation of SU2. Because if we can find such three matrices of any order n cross n, then, and if such that they satisfy this, then obviously this matrix, though it is not a SU2 matrix, not a 2 cross 2 unitary matrix, it is a 3 cross 3 unitary matrix with determinant 1, obviously, because J1, J2, J3 has to be traceless. If it is a 3 cross 3 matrix, it is an n cross n matrix with a determinant 1 and unitary matrix, then these matrices are somehow structurally contain in themselves the structure of SU2. Suppose, now think of this. You have a unitary matrix and whose determinant is 1, and suppose the matrix is n cross n. So this is a SUN group. Now you need n square minus 1 real parameters to specify the group, independent parameters. Okay. So this is the SUN group, say. Now each matrix here satisfies these conditions, these two conditions. Okay. Now all are n cross n matrices. Now, and obviously if they have n square minus 1 number of generators, SUN, new generators, so they will satisfy some Lie algebra. Forget about it. But this group contains in it, this group has a subgroup whose elements are obviously 3 n cross n and must satisfy this too. But suppose if they can be expressed in this way, where JAs satisfy this relation, then this subset or subgroup of SUN can represent the algebra of SU2, because within this subgroup every element, if every element satisfies, can be written in terms of 3 generators only. Clear? So now the question is whether it is possible how to get a higher dimensional group or set of matrices which satisfy the same Lie algebra of SU2. Clear? So that we are going to find out. So we are investigating now how to construct, whether it is possible to construct a higher dimensional higher dimensional representation of SU2. Okay. To construct this, so what we have to construct? So we have to find out three traceless Hermitian matrices of order n cross n, say n is such that these three matrices satisfy exactly the same algebra of SU3, though they are n by n. Okay, so we have to find out if we can find out these three matrices, then we have find out a higher dimensional representation of SU2, because all these any element constructed in this way will be a representation of SU2, but in higher dimension. Clear? Now suppose we assume that, so for this we will go by this way, assume that this JA, where A is equal to 1, 2, 3, they are Hermitian, traceless, and the commutation relation, Lie algebra. We assume this, and let's see with this assumption if we can find out some matrix. Then in the reverse way we can say those matrices will satisfy these conditions. Okay. Clear? The setup is clear?
Yes, sir.
Yes, sir.
Now we have assumed this. Now say first step is, now what I am doing here is purely, you have already done this while doing angular momentum algebra, but here I will do the same thing once again, just to I mean, in that sense it may be a recap of your angular momentum algebra calculations, but it will show you just by looking the entire thing in terms of a group or a representation of SU2, or how the angular momentum algebra, how SU2 represents angular momentum. Okay, we assume these three generators satisfy this. Now you construct a matrix. You can think of or an operator, whatever you say. This may be an operator who's like this. Okay, so these three are we have taken for granted, and now constructing something. Now you can easily check that using this relation you can easily check that J square commutes with all J1, J2, J3. You can prove this using simply this relation. Okay, because J1, J2 is I, J3, J2, J3 is I, J2. And such operators are called, and any operator which commutes with all the generators of a group are called, do you know? Casimir operators. Yeah. Okay. Secondly, define two operators J plus and J minus as a linear combination of J1 and J2. Clear? And you can check that. Checking things I am not doing because this is trivial, and you also have maybe done this in quantum mechanics class. So this J square, which is J1 square plus J2 square plus J3 square. So you can write half of J plus J minus plus J minus J plus J3 square. Because this J1 square, J2 square, you can write it this way, because if you take the product and this plus sign, you can see this will give you J1 square plus J2 square. Okay. Now see, I have three operators. One is, forget about the Casimir operator, J3 square, J3, J1, J2. In place of J1, J2, I have taken a linear combination of these two different linear combinations of these two. So the entire Lie algebra, which is expressed by this commutation relation, I have redefined these generators in terms of a particular linear combination of these three generators, J1, J2, J3, and get J plus, J minus, and J3. Clear? Now this object, so J1, J2, J3 are the three operators, or in we chosen they could have been represented by n cross n matrices, but they are, or take them to be matrices for the time being, n cross n matrices. Their commutation relation is this. Now we have defined one operator, another set of operators. This set of operators, generators, are just, these are just the linear combination of the original generators which satisfy this form of Lie algebra of SU2. Okay. Now you can check that again, because you know what is J plus J minus in terms of J1, J2, and you know the commutation relation between J1 and J2. Therefore, you can find out what is how this Lie algebra translates with this structure constant, translates in terms of these three operators, which are nothing but linear combinations of this set. I will do this later for any general group, how you can take linear combinations of the generator and create a new set of generators. Okay. Then J plus J minus commutator is equal to, you can calculate it, maybe you know this is 2J3, J plus J3 is equal to minus J plus, and J minus J3 is equal to J minus. Same as your angular momentum thing. You can directly check these relations if you define J plus J minus in this way shown in the previous page. Okay. Now, so you can see, you can tell that these relations are basically the commutation relations between the operators, and this structure is same as this. Only thing is that the structure constants, form of the structure constants get different here. Now, but this is also Lie algebra. because the general form of Lie algebra is XA XB equal to I F A B C XC. Commutants of any two generators is sum of all the generators, linear combination of all the generators. So here you take the generators as J plus, J minus, J3. So you can, this is a linear combination of all the generators. Only thing is that J plus, J minus coefficient are 0. Similarly here also. So this is nothing but another representation of the generators. Another way of choosing the generators. Clear? Only thing is that it will satisfy the same Lie algebra, but the form of the structure constant will appear in a different way if you choose different combinations of generators. Clear? This choice is sometimes is more powerful than this choice, because we will see that for a general group. Because these for physics problems where we apply transformations, choose this is a set of 3n cross n Hermitian matrices, stressless. You can linearly independent. You can choose a different set of linearly independent matrices out of the linear combinations of this. You can always choose that. Even in two-dimensional space, instead of choosing the 2 cross 2 stressless Hermitian matrices as Pauli matrices, you could have chosen a particular linear combination of them, 3 linear combinations of them, and choose these coefficients in such a way that they become linearly independent. You can do that. That will also satisfy, but they will satisfy, the structurally will satisfy these Lie algebra, but the structure constant will appear in a different form in that representation of generators. But it is the same Lie algebra. Only thing is that the form of the generators you choose, accordingly this constant will vary. This constant will be different. It will be a different constant. Clear? But this is the, you can construct innumerable number of such 3 combinations, which each of which is stressless and Hermitian. J3 is already Hermitian. J1, this is J1 plus IJ2. That is also, is that Hermitian? Hello?
Yes, sir. I think.
Which one, sir?
No, not Hermitian. Sorry, J plus dagger is how much?
J minus.
J1
1
plus
minus
IJ2 dagger. What is this?
J minus.
It is not Hermitian, sorry. J minus dagger is J plus, and J3 dagger is J3. So the new combination may not be Hermitian, but they're traceless anyway. What I'm saying is that this object, which is alpha 1 J1 plus alpha 2 J2 plus alpha 3 J3, this is a traceless matrix. It is Hermitian when alpha 1, alpha 2, alpha 3 are real. You can write this also in this form: beta 1, say beta plus J plus beta minus J minus plus beta 3 J3. This matrix is what? This matrix is traceless again, because J plus, but for this to be Hermitian, the coefficients need not be real. The coefficients has to be adjusted so that this thing is Hermitian, because this thing is Hermitian, this thing also should be Hermitian. So this new combination may not be Hermitian, but you can always express this object as this object. Only thing is that then these betas are not real. Okay, but we choose, our purpose is to construct, to find out whether J1, J2, J3 exist when the dimension is n cross n. Okay, for that we redefine a new set of generators in this way as a linear combination of this J1 and J2, and the Lie algebra translates in this form. Okay, now the same technique, since J square is a Casimir operator, it commutes with J3. The J square and J3 have these two matrices, if they exist, have simultaneous eigenstates, and we write them as J square as lambda m, J3 as lambda m, comma m lambda m. Clear? Where lambda m is the common eigenstates of J square and J3 because they commute. And you can also check that since J plus minus J3, you find this commutator. J plus J3 is minus J plus, J minus J3 is plus J minus. So you can, so this is in general you can write minus J plus J minus. Okay. Now using this commutation relation, you see that if you apply J3 J plus minus on lambda m, okay, so this will be from this commutation relation, the other term you can take that side and operate on it. So it is, you can check, this is J plus minus, this is the other term, goes to the other side, becomes negative, plus minus this term J plus minus on lambda m, and this gives you J plus minus m lambda m, plus J3 acting on this, plus minus keep this same lambda m, and finally you get m plus minus 1 into J plus minus lambda m. So this eigenstate lambda m is not an eigenstate of J plus minus, but J plus minus of this is an eigenstate of J3 with eigenvalue m plus minus 1. Clear? So this is an eigenstate of J3 with eigenvalue m plus minus 1. Just a minute. So J plus minus lambda m, this is an eigenstate of J3 with eigenvalue m plus minus 1. Now eigenstate of J3, therefore I can write, see, I can always write, because of this I can write J plus minus lambda m, which is an eigenstate of J3 with eigenvalue m plus minus 1, because lambda m is the generic notation for an eigenstate of J square with eigenvalue lambda, of J3 with eigenvalue m.
Something
স্যার
happened to it.
কি হয়ে গেছে আমার স্ক্রিনটা?
Huh?
আপনার
আপনার
স্ক্রিনে গাছ
স্ক্রিনে
দেখা যাচ্ছে।
পিকচার
স্যার
দেখাচ্ছে।
পিকটা দেখা যাচ্ছে না, একটা পেছনে একটা কি সব দেখা যাচ্ছে।
এটা এটা
পাহাড়
অন্য
দেখা
কারোর
যাচ্ছে স্যার,
picture।
পাহাড়।
এটা আমার নয়।
স্যার
হয়তো
আমি
pin করে।
মোবাইলে গ্রিড ভিউ করলাম আবার চলে এলো, ওটা অন্য কিছু হয়ে গেছিল মনে হয় আপনা আপনি।
হ্যাঁ, সবসময় গ্রিড ভিউতে রাখবে। এটা অন্য কারো মোবাইল থেকে আসছে, আমার থেকে আসছে না। এবার আসছে?
ইয়েস স্যার, ওকে।
So this object we have seen, this is an eigenstate of J3, sorry, with eigenvalue m plus minus 1, with this plus minus. And since this is an generic notation for eigenstate of J3 with eigenvalue m, so in place of, in m's place I have written m plus 1. So here I have to find out whether this state is an eigenstate of J square, and you can see that J plus minus contains J1 and IJ2, so therefore it always commutes with J square, Casimir operator. So this is J plus minus J square lambda m, and this is lambda into just, this is eigenvalue lambda, J plus minus lambda m. So J plus minus, this is the eigenvalue of eigenstate of J square is the same eigenvalue lambda, so I write it lambda here. Okay. Only thing is that I have to write a constant here. I don't know whether it is, I take this states to be normalized, I don't know whether this is normalized. So in general this is a function of C, lambda and m. Okay. Now we see that J1 square plus J2 square is equal to J square minus J3 square, because all of the sum is J square. Therefore, if you apply J1 plus J2 square on lambda m, this side you will get what? Lambda minus m square into lambda m. Clear? Okay. Now, so if you apply lambda m from this side, this is expectation value of this between lambda m, this is lambda minus m square. Because lambda m is, we have chosen them to be normalized, because eigenstates of J square and J3, common eigenstates, all these sets are normalized, we choose them. Because of that, this is this. Now, okay, let me ask you a question. Can you tell me, can you prove that this object is always positive from this relation?
Yeah, J1 square and J2 square are the positive operators. Their eigenvalues are positive.
No. J1 square's eigenvalue is positive. J2 square's eigenvalue is positive.
Yeah,
But
their sum is also
does-
positive.
no, they are operators. Their sum is no. J1, J2 do not commute. They do not have common eigenstates. So you can't give that argument. That argument is a very, wrong argument. Though it seems like this, because if they would have commute, then your argument was true. Then both have same eigenstates. Then its eigenvalue is positive. J2's eigenvalue is positive, and their squares will add up. But they do not have common eigenstates. This you can write as so where I have written.
Can we say that J1 square plus J2 square is a positive definite operators? So their expectation value between two states is always positive.
But positive definite, but then not commuting. Can you write J1 square plus J2 square in terms of, see, I can write this. I can write this always, because if you open up, you will get this. Okay, because I have shown this here, that right here. J square is this. So this is J1 square plus J2 square. This is J square. So this is J1 plus J2 square. Now if we operate lambda m, now it will become easy to prove. I told you to prove. Then it becomes lambda m j plus j minus lambda m plus lambda m j minus j plus lambda m. Clear? Now this thing is, this vector is the conjugate of this, because j1 minus dagger is j plus and vice versa. Therefore its conjugate is this. So this is basically of the form of psi. This way you have to show. So this is positive. Similarly this one. So you can say this. So this thing is a positive thing. Not because you cannot say directly like that. J1 square. See, so J1 square, if eigenvalue of J1 square is positive, that is, okay, if J1 is Hermitian, eigenvalue of J1 square is positive, eigenvalue of J2 squares is also positive, but they don't have same eigenstates. Clear? So that is because square of an operator, this is squared operator, that will not make you to tell this is positive. You have to go in this way. Is it clear, or can you follow, or?
Your logic is true, but I want to say that if we think J1 square plus J2 square as a whole operator, then can we say that J1 square plus J2 square, this full operator is a positive definite operator? So its expectation value between two basis states is
What
always
by positive definite operator?
their eigenvalues are positive always.
Their eigenvalues are always positive. J1 square eigenvalues are always positive. J2 square eigenvalues are always positive. So try to prove this. In general, if A has an eigenstate A, B has an eigenstate B, A, B are in Hermitian operators. Try to show this. Then you can surely say A square, you operate A on this side, so A square has an eigenvalue. B square will have an eigenvalue B square, and since A and B are real, A and B are Hermitian, their eigenvalues are real, their squares are positive. Okay. Now, just using this, now this is an operator. So by what is the, can you prove your statement that this operator will have positive eigenvalue? Why? That's the explanation I am asking.
Oh, okay. I see.
Its eigenstate is not A, neither B.
Yeah. Okay.
They do not commute. Clear?
Yes, sir, understand.
So we have seen that lambda minus m square is positive. So this is nothing but a, recapitulation of your angular momentum algebra, but this is inherent in SU2. I have never, I don't have to anyone who doesn't know about angular momentum, don't have to worry about this calculation. You can do it independently. So this object is always greater than 0, which means m or for a given lambda, m is bounded. So this is the conclusion. Clear? Then let for a given lambda, since m lies between this and this is bounded, let's m has some the maximum value of m is something. Let us call it j. It need not be root lambda. Maybe it is bounded between these two. Now, so j is somewhere in between these two, or maybe root lambda. I don't care, bother. But it has some maximum value because it is bounded. And I call this maximum value as j. Clear? Now, since we have seen this relation, is something like c plus minus a constant into lambda m plus minus 1. Acting on this state, it will raise the value of m or decrease the value of m by 1 unit. We have seen this from previous calculation. So I am not using any result which is not done here. So if this is so, then I can write j plus lambda j, where I have put for given lambda, this is the maximum value of m. Okay, what it should be? It should be j for j plus, it should be
0.
m should be j plus 1, but it is the maximum value. So there are no states which is above this. So this relation can only hold when this entire thing is 0. Clear?
Yes, sir.
Now you apply J minus on this. So this is also 0, J minus. Now J plus J minus, this thing you write so J plus J minus is J1 plus IJ2. J minus J plus is J1 minus IJ2 into J1 plus IJ2. What is this? J1 square. This is plus J2 square plus I J1 J2. Okay, completed. And this is J1 square plus J2 square is J square minus J3 square. And this is I J3. So this is J3. Okay. So this is J square minus J3 square minus J3 lambda J equal to 0, which will give you J square on this is lambda minus this is J square, J is M square minus J. Since this state exists, so this thing should be 0. This number should be 0, which tells you that lambda should be J into J plus 1. So lambda is related to the maximum value of M by this relation. J is the maximum value of M. Yeah. Now we are slowly progressing to what we want to show. Similarly, you can see since M is bounded, M will also have a minimum value. Therefore, let's choose M minimum value as J prime. Okay. If it is J prime, now you know this lambda of J prime is a minimum value. So J minus operating on this. So action of J minus is what? It will lower this value, but this is the minimum value. There is nothing. So this thing will be 0. Clear? So in the similar way, if you apply J plus J minus on this, you will get 0. And writing this, you can see this you can write as J square minus J3 square. Here it will be plus J3. Or lambda minus J prime square plus J prime is equal to 0, which shows lambda is J prime into J prime minus 1. Clear? So lambda, the same lambda is related to the maximum value of M. Maximum value of M by this relation. Same lambda is related to the minimum value of M by this relation. Therefore, they should equal because both are equal to lambda. So maximum value and minimum value are connected by this equation, and you can see that this equation will give you, if you just multiply and J plus J minus into J minus plus 1 is equal to 0. Here, if this is 0, any one of them is 0. Therefore, this cannot be 0. Because why this cannot be 0? Can anyone tell me why this cannot be 0?
Because J cannot be 0.
Yes, because no. This cannot be 0 because J prime
J
is the
can't
minimum
yes,
value of N. It is always less than J. But if this is 0, then J prime becomes J plus 1. So J becomes more than J. So since this is true, this cannot be 0. We must have J plus J equal to 0 or J prime is equal to minus J. Which basically tells you for a given lambda, the M, if M max is J, M min will be minus J. Okay. Now look at this relation. Look at this relation. J minus Jm is equal to some constant lambda m lambda minus m. Sorry, m minus 1. It lowers this state. So if we take this lambda and these m values which are now bounded between J and minus J, clear? It is the maximum value, it is the minimum value. So if you take this and operate this, what will be the result? Some constant into lambda J minus 1. Clear? Now so this is a state. Now if you operate J minus again on, so it will be another constant into lambda J minus 2. In this way, where you will end? When you reach, so J is decreasing upon each operation of J minus. So in this way, when you reach J of minus J, the result will be 0 because there is nothing below. So all these states, now give your concentration because these things are you already know from quantum mechanics, but now come all these states clear for a given lambda.
লাস্টের টার্মটা মাইনাস জে হবে না?
Just a minute. So you see all these states are attainable from one to other by operation of J minus many times. Now this many times means integer number of times. So J minus of minus J. Okay, J decreases by 1 unit, 2 unit and reaches minus J. Okay, so this object must be an integer. This is the argument because you apply it by operating J minus many times. After how many times you will end at J minus J lambda J minus J, that many times is an integral number. So either 2 times or 4 times or 10 times like that. So that integer, so J minus J, because so J is such a value, J must be of such a value that minus it can reach to minus J by integral amount. Clear? For example, if j is say for 3.1, then minus j is minus 3.1. Now, if you keep on operating j minus, it will be down by 1 unit, 2.1, then 1.1, then by 1 unit, 0.1, then 1 unit, minus 1, minus 9, then by 1 unit, minus 1.9, minus 2.9, minus 3.9, like that. But never, minus 3.1 will never be reached. Clear? So j cannot have any value. J's value is constrained by this condition. The condition is 2j has to be an integer. Clear? Or j can be an integer by 2. That means either it is even or odd. Integer or half integer. Clear? Is it clear?
Yes, sir.
Okay. So this is this. I give emphasis on this. So this is the key of constructing higher dimensional representation of SU2. Let's see how. So let's try. So consider this state j comma m. What is this state? Where this state lambda, this lambda I can write in terms of the maximum value of m by this. Okay. So instead of marking this state by lambda, I have now put j here. So jm is same as lambda m. Now how many possible values of m are there now? Minus j plus 1 up to plus j, or you can do the reverse way. So there are 2j plus 1 values of m. Now think of these states. First value is, highest value is this, next value is this, end value is this. So there are 2j plus 1 such states. Clear? Now all these states are what? Orthogonal states. Why? Why all these states are orthogonal? Anyone? Can you tell me the argument why all these states are orthogonal? You have done this in angular momentum algebra in quantum mechanics. So why all these states are orthogonal? What argument I should give to prove this? Or they are not orthogonal? Hello? I will not proceed unless I get the answer. This is the basis of construction of higher dimensional representation of SU2. Why these states are orthogonal?
Because they're eigenstate of angular momentum.
Yeah, because they are eigenstates of J3. and J3 is a Hermitian operator. All the so they are eigensets of J3. They are also eigensets of, just a minute.